Welcome. In this particular reasonably short talk, we're going to introduce AI-controlled forms of movement. In particular, we're going to have a look at what's known as kinematic forms of movement. Kinematic forms of movement, they're one of the more simple ways of getting the character to move around. Another way of thinking of them is in terms of instantaneous forms of movement, that we will have objects that will abruptly change their particular velocity or the direction in which they're travelling. And the types of movement we'll look at are things like chasing after something, or running away for something, or trying to arrive and stop at a particular point. After this, we're going to have a look at what's known as steering algorithms, and they provide an output acceleration, so they smoothly and continuously change the velocity of the orientation. And we'll look at a wider range of movement capabilities when we're looking at steering algorithms. So by way of introduction then to movement AI, a fairly simple notion. We've got AI controlled entities, and we want to give them the ability to move around the world that they find themselves within. And obviously enough, there's going to be information about the other entities and the objects within that world that we want to provide these algorithms with, so they have something to work on. Some of the algorithms, and the one we're looking at certainly within this talk, they're going to be quite straightforward, quite simple. They're broadly just going to know whereabouts you're at and where you want to get to. Some of the other later algorithms we'll have a look at, they'll be a little bit more sophisticated, things like pathfinding, where we'll take into account obstacles that are in our way and how we can move around them and calculate an intelligent path to our destination. For these types of algorithms in this talk, as mentioned, they're kinematic. They will give us an output velocity, and so the objects that are using these types of algorithms will instantaneously change their velocity. It's not going to be a smooth change, they'll just abruptly change the velocity. For some games that's perfectly fine. For other types of game, for example, let's say a racing car game, it isn't. And you want really use accelerations there that gradually change the velocity and change the position, so they're more smooth in terms of movement. But we'll have a look at those in the next talk. Both for kinematic and for steering behaviour, we're going to have to introduce or assume a few properties of our game entities. Obviously, they're going to have a position, whereabouts they are within the world. For some game objects, well, they'll all have an orientation, but for some game objects, actually we'll want to change the orientation or the rotation of the object. How we update it really does depend upon the game. If it's a tile-based setup, we may just simply move it from one tile to another tile very directly. Other games, we want to have the nice, smooth, continuous motion. But what we're assuming here is that for all of our objects, we will have a vector. 2 dimensions is going to be an x and a y component to it. One for the position, and another vector for the velocity, which is the rate of change of position. We're also assuming that we will have a single value for the orientation, which is in what angle it's facing, and another value beyond that for the rotation, which is it's the rate of change of orientation, how quickly it is rotating around and moving in a certain direction. For the steering algorithms, we're going to enrich this by adding in acceleration. So we'll have an acceleration vector, which can update our position vector or via the velocity vector. We'll also have an angular acceleration, an ordinary scalar value, which can update our linear rotation and update the orientation in turn. As to how we update these things, because we're calling update frequently, many times a second, it means we can get away with using a simplified form of updating, for example, the position given a velocity and acceleration. There's a set of equations known as Newton-Euler equations. There's a couple of simplified forms you can see over here on the right-hand side. As mentioned, because we're calling this frequently, many times a second, we can get away using the simplest forms. And they are very simple. We'll have an acceleration. The acceleration will be a certain number of changes of units per unit time. So maybe 2 meters per second. So we're going to update our velocity using that. we will scale it with the time delta, which is how much time has actually elapsed. So our accelerations will be, for example, per second. So we want to take into account, well, what sliver of a second is this particular frame. Having updated the velocity using the acceleration, we then use the velocity to update the position, gives us our final position. And likewise with rotation and orientation, we'll have an angular acceleration, which will update our rotation, and in turn the rotation will be used to update the orientation of our particular device. So we're going to assume we're going to have a basic element or object within our game that embodies these properties and embodies this form of update. We'll have a look at a couple of simple kinematic algorithms. It's really by way of showing you a few simple ones, and we can then build upon these when we get on to looking at the steering behaviours. So we're going to have a look at three simple forms: seek, flee and arrive. Seek is where we will head at full speed towards our target location. Flee is where we will flee away at full speed from whatever position we're fleeing away from. And arrive is where we will move towards a target position, slowing down and then stopping whenever we get to that target position. As a reminder, these are kinematic algorithms, so there's no notion of acceleration here. We're simply going to output a target velocity and then use that velocity to update our position as we go through. So I'll start off using seek first of all. We're going to assume that we have a current position where we're at. We're going to assume we have a target location where we want to get to. And the output from the algorithm is going to be a velocity that shall take us from where we're at to where we want to be, where we want to get to. It's a fairly simple piece of code you can see here. It's down in the bottom left. The fragment of pseudocode, I suppose, on the right is a little extension to this. It's generally speaking, if an object's moving in a certain direction, we may want to make sure its orientation is also aligned along that direction. That's particularly true for things that are sort of top down, where if an object's moving, say 45 degrees, moving up the screen to the left, we want to make sure it's also pointed in that direction as well. So for the seek algorithm over on the left hand side, for parameters we're taking in a vector whereabouts we're at, we're taking another vector where we want to get to. And because we're outputting a velocity here, we need to have some indication of, well, how big should this velocity be? So max speed is going to be how fast we're moving towards our target location. It's really one line of pseudocode, which corresponds to a couple of lines of actual written code, but one line of pseudocode here. The velocity that we're going to output, now remember, velocity comprises two components. It has a speed, a magnitude, and it has a direction. So velocity is moving at a certain speed in a certain direction. So the first bit, target minus source, and the normalized version of that gives us our direction. Now, target minus source, this is sort of vector manipulation. We are working out the difference between the target point and the source point. If it's two dimensions, we'll have an x and a y component to this. So it's basically taking away the target at y minus source.y, and also target.x minus source.x, and giving us a two-component vector. That particular target minus source, if you were to think about drawing down a piece of paper, it gives you the vector from the source leading to the target. Now that's sort of, if you like, the vector separating the two. If we normalize a vector, what that means is that we keep pointing it in the same direction, so the direction doesn't change, but the length of the vector changes and it becomes of length 1. So any normalized vector can point in any direction, but it must have a length 1. And that's quite a useful property. It's also known as a directional vector, that it points in a direction, but because it has a length of 1, you can do nice things with it. We could, for example, multiply it by max speed in this particular case. And if we do that, what it means is that we have a vector that points from where we're at towards the target we want to get to, and the length of that vector, which is a velocity, is the speed at which we want to move. And we simply return that. So a little piece of code here will work out where we go and then scale that based on the speed that we want to take us to that particular point. Over on the right hand side for the determine orientation method, here is a simple method. We pass in a velocity. This is the velocity we currently have. We also pass in our current orientation, how we're currently oriented, and we will be outputting from this our new orientation, the orientation that if we select or move to, we will then be pointing along our velocity, the direction that our velocity has taken us in. So we're going to check here, firstly, within the if we have zero velocity, in other words, we're not moving, then it's just return the current orientation. We shouldn't be moving, but we're not changing. Other than that, we're going to return, and it's a function built into basically all of the MAS libraries, be it Java or C#. It's known as atam2 or arctam2. And there's a comment in the next slide, we'll talk a little bit more about that, but basically we pass in the x and the y components of the velocity. You can tweak them slightly depending on the coordinate system, and this will give us the angle, the orientation that we should set ourselves with to align with that particular direction. The counterpart to seek is flee. It's really the opposite of seek. In other words, we move away as fast as we can from the particular target. And if you have a look at the definition here of the flee method, you can see it's remarkably similar to seek. The only difference, and it is a single difference, is instead of doing target minus source, we do source minus target. So we end up with a vector that's at the same length as before, but it is pointing in the opposite direction. So that's the only change to it, and there you get a vector not pointing towards the target, pointing away from the target. And we will normalize that down to length 1, and we'll then scale it up to the actual maximum speed that we want to move away with. So in terms of the aside here, arctan2. Now, arctangent, tan is a little adjacent, is one of the trigonometric properties. So if I give you an x and a y component, they're part of a triangle, using arctan, I can work out then the angle that takes me up if this were part of a triangle, in other words, the orientation. Arctan, it is a cyclic function. It repeats with a certain period, and the period is every 180 degrees. You have the same pattern coming out of arctan, and indeed sine and cos repeat at 180 degree cycles as well. 180 degrees, okay, it's useful, but it's not useful enough, because if we're thinking about a full orientation, it's 360 degrees. Now, we're talking here about degrees. A lot of maths is done in terms of radians, and 2 pi radians is equivalent to 360 degrees. So if you look down, the normal arctan function returns a range of minus pi over 2 to pi over 2. That's the same as saying minus 90 to positive 90 degrees. Whereas arctan2 returns it in the range minus 180 to 180. So it's a full 360 degree orientation. So arctan2 we will be using when we want to take a direction expressed as a vector and to work out what particular angle orientation does that correspond with. We'll next have a look at arrive. Arrive is related to seek, but it's in some ways an improvement. One of the limitations, and it depends on its use, whether or not it's a meaningful limitation. One of the limitations of seek is that it always goes at full speed, or whatever speed you specify, towards the target. That means that if you specify a particular point that's not moving, seek is likely to get to it and then jump over it and then jump the other way and keep basically skittering around the point, never getting to it, unless it's particularly likely just to stop remarkably on the point. So we want to improve seek. We want to improve it in a couple of ways. We want to give a region that if we are sufficiently close to the target, then we're happy to stop. So as opposed to getting to the very, very, very precise location, if we're within 0.01 of it, then we're happy not to move, or we've reached our target. The second change we'll make is that as we get closer to the target, we'll slow down. So it doesn't immediately go to it and then just slam on the brakes. Rather, it approaches it, slows down, and then stops whenever it reaches our target zone. So an example here where initially we might have a maximum velocity when we're far away. As we're getting closer, we'll start scaling the velocity down, slower and slower and slower, until we get within our closeness threshold, and we'll at that point have decided that we're sufficiently close to the target that we can just stop. In terms of the code that does this, it's as can be seen here, so it's a little bit more extensive than the other one, but it all comfortably fits on one screen's worth of code. We're taking in our source vector, where we're at, our target vector, where we want to go to, the speed, the maximum speed that we're willing to travel along that, so far the same as seek. Another addition to this then is the near radius. So this is the distance within which we're happy we're close enough, we're just simply going to stop. Now what else do we have within this? We have a slowing factor. Now it's defined within the method equally. You could pass it in as a parameter to it as well if you wanted the caller to have control over it. This is going to be the measure of how quickly we slow down. Do we slam on the brakes and slow down very, very fast? Do we sort of gradually slow down? So it can be, if you want, a configuration parameter on the method. We have our output velocity that we will be returning, and we initially set off with an output velocity of 0. So we're not accelerating any way whatsoever in terms of our velocity. So that's our starting gambit. We then work out a separation vector, which is target minus source. That gives us the vector from the source that will take us out to the target. Remember, for any particular vector, a couple of useful things is the length of it, which would be the distance in this case. And if you normalize it, that gives us the direction. So we're going to check, after we've calculated the separation vector, are we sufficiently close that we're happy that we've reached the target? So we go to the separation vector, we ask what's the length of that vector? And if that length is less than whatever the defined near radius is, in other words, we've got sufficiently close that we're within our comfort zone. At that point, we simply return the velocity. And remember, we've initialized it to 0 a few lines above. So we really are just returning 0 velocity. If that if isn't true, what it means then is that our distance away from the target is greater than or equal to the near radius. So we have a bit of work still to do. So we're going to head towards it. So we work out initially velocity is equal to separation divided by the slowing factor. This is a way of having a guess at the velocity. And basically, the further out we are, the faster we're going to try to move towards it. And that's where the slowing factor can come in. That will control how quickly or at what point we want to start slowing down. Now, the line is stated could be problematic. If we're very far away, then separation is going to be quite a large value, and we could end up with a very large velocity, one that's larger than the maximum speed that we're prepared to move along with. So we check here to see that, okay, well, we'll have a guess at the velocity. If the length of the velocity, now the length of a velocity vector is the speed, is another way of putting it. So if that speed is greater than the maximum speed that we're prepared to go at, we do the normal thing. We normalize the vector, so we're retaining the same direction. Unit length, we multiply that, we scale it up then by the maximum speed. And finally at the end, that's what we return. Reasonably straightforward, but also reasonably effective in terms of how it operates. So by way of takeaways in this, there's a couple of them you can see here. For AI controlled entities, a lot of them are going to want to move about, so we need to have some way of enabling them to move. And that's where our steering or kinetic algorithms will come in. What we looked at here was a few simple forms of kinetic movement. It gives you instantaneous changes in velocity, so there are abrupt changes in velocity, and for some games they're perfectly fine. Other games they are not, but they work by way of giving us some control over how the objects move about within their particular world.